shell so that we can analyze the local stress, do a local stress analysis. And then going on, we have support services for heavy lifts and that sort of thing. And revamp service. I think probably one of the things that we forget to talk about a lot is that we do a lot of revamps, and we have in the past, and we do right now, do a lot of revamp work. So you have existing equipment, and that's actually, it takes a lot of time because you have existing equipment, so you have to research and find out what you have out there. A lot of times the information that a lot of these refineries and whatever companies that we work with, they're not real good. And a lot of it's really old, and they want to use stuff that's old, and a lot of times people get great ideas to do something on something that's really old, and a lot of times it's not a good idea. So, go on. Okay, this is the general workflow, and probably I can't read it from here. But we receive the job scope, and we take a look. We look at the basic process package, and from there we start to prepare the vessel specifications, because from that information we can find out where the job is at, what some of the design criteria is, and that goes into the vessel specifications. We prepare a vessel design criteria, sometimes a checklist that defines what our design requirements are going to be. And some of that is dependent on other people. We prepare the vessel design and drawings. From there, now that sounds like an easy thing, the vessel design and drawings, but we do calculations, and we do a lot of things. We prepare the inquiry package, and then after that, when we actually get the bids, then we analyze those bids. And in the meantime, if there's any special designs, we do those. And then eventually we get orientations, and we put those on the drawings, and then after that's all submitted to the vendor, then we review all the vendor drawings, and we place the order, and we check all the vendor drawings, vendor data, vendor calculations, and that's for the most part, that's the general work scope that we do. So go ahead. So this is just another, this is really the same thing. So we have, we look at the work scope, we prepare the design criteria, prepare vessel specifications, prepare the design and drawings, do the inquiry package, analyze bids, special designs, add the orientation, and review vendor drawings. Okay, go ahead. Okay, at this point, when we talk about receiving and analyzing the job scope and looking at we get certain information from various groups, and so we depend on the process group. Gives us a lot of information to begin with. So we get our equipment data sheets, process flow diagrams. And P&IDs, those all come into play, and we look at all that information. And from the project staff, we get the job scope, the job criteria, client specs, and overall schedule. And again, from mechanical process, we get the design data sheets with the skirt height and that sort of thing. And then, of course, you get the materials diagrams. And I think one of the things that impacts us from the structural group and from client specifications is the structural design criteria. A lot of mechanical equipment, they don't worry about the structural design criteria that much because they're heavy and they're low. And pressure vessels are generally light, relatively, and they can be quite large. So that means that things like wind and seismic become a big factor. So we have to be mindful of those requirements in the design of the pressure vessel, because it's not as simple as it is for a lot of the other mechanical equipment, because they're mostly concerned on whether the anchor bolts will hold. So, you know, you have something that's fairly heavy and that's low to the ground. Really, the only thing is that you've got wind is not a concern, and if you have a seismic event, you really are just worried about shearing your anchor bolts off, so it's not going to tip over on you for the most part. But for pressure vessels, that's not the case. They do tend to tip over. So, go ahead. All right, this is an example of an equipment list. So we get the equipment list from the process group, and that's usually one of the earlier things that we get along the way. And sometimes we've been known to actually kind of work off these a little bit to try to get things going early on, but it's really not a good idea, because we're supposed to wait until we get a little more concrete data. But from time to time, we've been forced to kind of work using this data here. So you can go ahead. Okay, P&IDs. P&IDs, of course, are a very important aspect of the overall development of a project, and from our standpoint, it really defines the requirements. It's really when things become more concrete for us when the P&IDs are issued. So we always want to look at these so that we make sure that the line sizes coincide with the nozzle sizes that we have on the vessel, and if they don't, why not? And those kinds of issues. So, and things like whether the skirt has to be a certain height for pump out reasons or whatever. We need to know that information, because it's very important. So, and then we get a process data sheet, and this really usually outlines the design requirements. Sometimes they're not that complete, and sometimes we have to go back and ask questions, but that's part of the job work. That's part of the process. But this is what that generally looks at. And again, it looks like, again, this is something that we do check. We come back and make sure that all the connections and the sizes and the number of trays, those kinds of things are all the things that we check to make sure that they are consistent with not only what we're going to put out, but also with the P&ID and any other data that's available. And this is just the second one. Okay, specifications. Specifications. Often clients have their own specifications, but not all of them do. And in fact, on recently the SUMS project that I've been working on, we had to write all our own specifications because they don't really have any. So this is a part of the process that actually takes quite a bit of time, because even though we have a template, often the particular requirements of a particular company, even though they don't have their own specifications, they always are specific about certain things that they want to see in the design. So we have to make sure that we meet all their criteria and meet the expectations of the client. And this is true of really all the specifications. So we write, the vessel department will write the pressure vessel specification, ladder platform specifications, and tray specifications. Now we do rely on materials applications to give us installation specs, and material applications to give us painting specs. And then we also rely on the structural group to give us the structural design criteria, which often is transferred into the vessel specification as well. Okay, go ahead. From there, we start to prepare the vessel design drawings. And before we do that, we do calculations. Now, the calculations that we do are for a couple reasons. At one point or another, they're going to ask, somebody's going to want to know how much this thing weighs, and they want to know, they may want to know some idea of cost. And if you do a computer calculation, you can figure out how much it weighs, and you can maybe do an in-house estimate, and if not, you can sometimes get estimates from certain vendors. But we do the computer calculation for not only that reason, but we also do a computer calculation for the structural group, is so that they can start design on the foundation if they want to do it. So we try to do a very conservative design. That is, we have an idea of what is going to be a lot of the worst case loads. So we take the loads that we get for seismic and wind. We take some estimates of what we're going to get for platforming at this time, because we don't know what kind of platforms we're going to get. But we have an estimate on what we design for on that basis. And we come up with a design, and that should define the anchor bolt requirements and the base plate requirements. Do we give that to the structural group, and then they will confirm the anchor bolt requirements, and they can design their support system. And so that's what we do to begin with. From there, we do general arrangement. We create a general arrangement drawing. After we created that, we sent it out for squad check. After the squad check, we incorporate the comments, and then we issue the drawing for quote and purchase. So you can go ahead, Amy. Now, this is an example of a particular vessel that we did on Action Thumbs. And as you can see, I picked this vessel because it's tall and skinny. And we don't get a lot of these, but when you have a vessel like this that's tall and thin, we're in a high earthquake zone, because this is in Long Beach, you end up with a couple things that you have to consider. One thing is wind and what's called vortex shedding. If you've ever driven down the road at a high speed and you had a car with an antenna, you'll notice that the antenna is doing this from the wind. Well, that's called vortex shedding. And you have to be concerned with that if the ratio between the diameter and the height, if it's greater than 15, vortex shedding is a consideration that you have to account for. Also, you'll notice something a little odd on this one. The skirt is flared out here. Now, the reason that the skirt is flared, this is another aspect of the design and the information going to both the structural group and piping group and plant layout, is if we need to have a skirt that's larger than the diameter of the vessel, they need to know that for the plant layout. Otherwise, it's going to take up more space than they think it is. For instance, this vessel is nearly 100 feet tall and it's 4-foot diameter, but the skirt is about 9 or 10 foot diameter. I don't recall what it is exactly. But the reason that the skirt gets large is a function of the number of anchor bolts required to hold it up, the number and size of anchor bolts. So we try to design this to meet the certain requirements that not only the structure group has for anchor bolt spacing, but we need enough anchor bolts to keep this thing from turning over on us. So you can go ahead. This is an example of the pressure summary from this is a compressed program that we use. And as you can see, it defines what the design pressure is, the design temperature, the maximum allowable working pressure, the maximum allowable pressure, the maximum allowable external pressure, and various other things. And the minimum design metal temperature, and it tells you certain limitations of what it is, if there are limitations, and there's notes here. So it tells you a lot. And actually, this is just an excerpt from, this is just the summary report. It actually does, like hundreds of pages. It's a terrible printout. but anyways, it does print out a lot of information here. But this is just the summary, so you can go ahead. And again, this is a thickness summary, so it tells you, you'll notice here that as you start from the top, the thickness is quite thin, and as you work your way down, it gets thicker and thicker, and it's a function of the bending moment on the vessel, because it is tall and skinny. As you get down lower and lower, the longitudinal stresses keep getting higher and higher because of it wanting to overturn relative to the seismic forces. In this case, it was seismic forces, I believe. Yeah, it says it's governed by seismic here. And so as the seismic forces increase, as it gets farther and farther down the shell has to keep getting thicker and thicker in order to accommodate those stresses. So you can go ahead. This is a weight summary sheet. This right down here, it's cut off a little bit, but it tells you what the weight of the vessel is, and operating weights, operating corroded, operating new, empty corroded, empty new, that sort of thing. So but it gives you a breakdown. And the good thing about this too is that if you go through this, you can see where all the loads are coming from. So when you read through it, you can kind of see, well, we've got a certain amount of loads here from trays and supports. We've put in certain loads from ladders and platforms. We have any other just vertical loads. So here we've got a 4,000-pound vertical load that we put in for something that we thought was required. So these are a lot of times these are estimated values. So at this point of the design work, so you can go ahead. And this is just finishes up the page. And then this doesn't happen to be all the nozzles on the vessel, but if you did input all the nozzles, this would list all the connections on the vessel, and it would tell you what the materials are, and it would tell you what the flange rating is and all that stuff. So again, this is a nozzle summary. So this is a little more on the pressure rating of the nozzle, of the nozzles that we have listed here. Now this is the same vessel, and this is the type of outline drawing or data sheet, whatever you want to call it, that the vessel group develops to get ready to purchase a particular item. And up here is the design requirements that you would see in the data sheet that you get from process. But beyond that, we've defined certain things like what materials we want to buy, and we've clarified that to the vendor what exact materials we want to purchase. This happens to be made out of 304L stainless steel, so we've defined that material. We define on whether we're going to have clips for pipe supports, pipe guides, fireproofing, whether we're going to have fireproofing, insulation supports. All these kinds of things are things that a fabricator needs to know, because if we're going to ask for a price from him, he needs to know what he has to quote. If he doesn't know what he has to quote, he's going to give you, you're not going to get the right answer. You're going to get a price that's not right. And this is information he needs to know. Just like the number of connections and the size, he needs to know that. He doesn't necessarily need to know where they're at this point. He just needs to know how many there are and what size there is. And then we have some general notes here. Some of it here deals with wind and seismic criteria right here. And then we have some other general notes that we put on drawings. And if there's anything special, then we try to define it on the drawing. So. Sure.
area in such probe vessel, in your computer model, the seismic force, for example, would affect the stresses in the shell of the vessel?
That's correct.
Or that would be used for the anchor of
It's all the case. It's those forces go all the way down to. In fact, I should have. Can we go back one? Normally, I kind of messed up a little bit here. I should have put the printout that we get on the anchor design, and the anchor design gives you the overturning moments, the weight at the anchor, shows you what the moments are for wind and seismic, and the anchor bolt sizes and all that stuff. So that's something that the design does do. You can go ahead, Amy. And we define that information right here for the anchor bolts and the bolt circle and all that information. But all the loads, all the loads are carried down to the base plate. So the skirt is designed for those seismic loads, and the shell, of course, is.
So if you run your computer model without the seismic and then run to the seismic, you take an element of the shell and you check the stresses will be different.
Substantially different in this case. Yeah, because this one is particularly tall and skinny, so the loads here due to the seismic are quite high. So it really increases the thickness from what was it, 1.5 to from 5/16 up here to 1.5 inches down here. So it's quite a difference. Okay, so from that drawing and from the other data, from the standard drawings that we have, from the specifications that we've developed, we put together an RFQ package, a request for quotation package, and that package is it goes through the signature cycle. So it goes through the financial group, scheduling, quality, project, and client review, so the client can sign off on it. And eventually it gets to procurement, and procurement will combine that with the commercial requirements, and then they send that out to prospective vendors, and we wait a few weeks. And after we wait a few weeks, we get some prices back. And so from there we go going on. Let's see, where are we at here? Okay, so when we get the prices back, then we have to analyze the bids. Okay, so procurement gets the bids, they receive the bids, and we get. Now it depends on. Sometimes we get what the prices are, sometimes we don't. It really depends on the particular procurement group and probably sometimes it's client preferences. But from there, we do an analysis of what we know about particular vendors, particular fabricators, and we look at whether they're meeting the criteria, the design criteria that we've identified in the bid that we put together, in the technical data that we've required, and we check all that stuff, and we send that back. That goes back to the purchasing group, and then they put that together with their monetary analysis and whether they have the commercial terms, whether everybody's happy with the commercial terms and client approval, and out of that comes somebody picks who they want to go to, and you can go on. This is an example of a bid analysis. What we've done is we've taken the requirements and listed them, and then we've gone to each vendor and made sure that they've, in their bid, that they've covered each one of these aspects. So it's a little bit time consuming, but we try to make sure that we cover all the pertinent information and design requirements that we feel that the vendor needs to meet in order to be a successful vendor for this project. So, go ahead, Amy.
What if the bidder doesn't include that information?
Then potentially he gets thrown out. Yeah. Oh, break? Let's wait a minute. Soon enough. Let's see. We're on 6. Design special support select. This really is. I should have probably shown an example of this, but a lot of times we get special conditions. For instance, let's say we have a vessel that has a reboiler hanging off of it, and we have to design a special support, and sometimes it could be thousands of pounds of extra load that's on the side of the vessel. So we have to design that, make sure that the local loads in the shell are not too high, and make sure that the structural steel that we've provided is strong enough to hold the load. And so we do that. Also, we check if there's any special lifting requirements that we might have to engage in, and just the overall design. We can go back and make sure that there's not anything that's going to come up on us, and especially for lifting. Lifting can really be an issue, especially on that particular vessel that we were just talking about is long and thin and skinny. Lifting can be a big issue. So you can go ahead. We add the orientation to the vessel. Now, we get information from the piping group on where they want to have the nozzles. Now, we have to check where those nozzles are located relative to the internals in the vessel. For instance, if the vessel has trays, we have to make sure that the nozzles are in the right location so that it will function correctly. We make sure that there's no interferences outside the vessel relative to the ladders and platforms. And sometimes the platforms that piping comes up with are difficult to make work, but we try to make them work if we can. And sometimes we have to go back and say you can't do this because it's not reasonable. But this is a big checking period for us, because we add the orientation onto the vessel, the elevations of the connections on the vessel, and we check the locations of everything to make sure that we don't have any interferences. And going on, this is an example. This is the same vessel, by the way. This is an example of the information that we get from piping on what the orientation is. So I just kind of wanted to show that to you. You can go ahead. This is just another example of the same vessel. And as you can see, it's kind of a combination of computer drawing and hand drawing. So this is what we get. We do our design off of this information. So you can go ahead. Okay, now we have that information. We have where the nozzle locations are. This is what we produce. We go back through and we locate all the nozzles on the plan view where they are, and then we go through and we locate all the nozzles on the elevation view. Now, ideally, we try to do this all to scale when we do the drawing, so that when we put these nozzles in and we check the elevations, we're actually checking where they are, whether they miss things. So it's always a good idea to do that, so that we make sure that we're missing things, we're missing the components inside the vessel, and we're not hitting anything. So go ahead. Now this is what we get for the platforming, and it's the same kind of thing, kind of a combination of computer and hand-drawn sketches. And from that we start to build the ladders and platform design. And we do, you can go ahead, Amy. And again, you can see this gives us the diameter of what they want the platform to be and where the ladder is located. And this is, again, the same vessel. So I just wanted to show you that this is the type of information that we get from piping, and we do our design on this. So you can go ahead. And it sometimes changes a little bit. If you, when we get down here a little bit farther, go